Thank you, Ziyang. All right. Welcome back, everyone. So this is the last practical session today, and I'm sure everyone's happy to see the backside of unsupervised learning because this week was solely about weekly supervised learning. And I kind of, during the lecture sessions, I introduced multiple instance learning, which is what we're going to really focus on today. If you haven't looked at the videos and you need some background for today's practical session, I suggest you kind of skip to the multiple instance learning part and just understand the idea of bags and instances and how they kind of combine together. So rather than going through a quick recap, I'm actually going to dive into the details of today's session so that you can get all your questions out the way and really get an understanding of what you're doing today and get stuck in. So I mentioned in the video that we'll be tackling this particular paper, which is MIL pooling, but with attention. And it's done by Max Wellen's group in Amsterdam, and it's a really nice paper and shows some really good real-world examples of using this particular method in the medical field, which is how I came across it myself. I've also came across multiple instance learning in my earlier days when I was doing more traditional machine learning, and it's just really suitable for a lot of tasks that we come across in the medical field as well. And that's both in text data as well as image data, not just image data, which is shown here today. So the idea of multiple instance learning is to extract a label for multiple instances of a single label for multiple instances by using a single network as well. So here the authors kind of described in the introduction that they're analyzing very high resolution images called whole slide images in histopathology. And because they're very high res, there's no way to actually push it through a GPU all at once. And I've had the same issue myself. So we usually need to get creative about the ways we push these images through a network. Usually what's done is you randomly extract patches from these slides and just hope that you've somehow captured what needs the important parts within those few patches. Here they've kind of weighted quite a few number of patches together in order to come up with one label. So we have one label for the whole slide image, and we've got multiple patches extracted from a whole slide image, but no labels are given for the patches, only at the slide level. So you've basically got lots and lots of images and only one label attached to lots and lots of those little images. And really the task of your network is to figure out which of those instances are reflective of the label and which ones are not. So this is a figure that I took from the paper itself, and it shows this is actually a patch that's taken from a whole slide image, but similarly it's a very high resolution. You can see all the little patches that were extracted from this one image, and this is kind of the ground truth. So we want to be able to capture these patches here, which are reflective of cancer, and kind of ignore the areas that are just containing healthy tissue. And you see some of the results down here as well, where they've kind of applied this transparent alpha overlay showing you which patches were really important for the label and which patches were not. So you're going to kind of recreate this today. This is an image of the MIL pooling architecture that you're going to tackle today. There's a few different things that need to be implemented in order to get this whole network up and running. So first of all, we're going to kind of replicate the paper. So please feel free to use the paper as a reference guide. And also the slides that I'm going to show you just now, I'll put them onto the shared drive as well, so you can reference that whilst you're going along. So the first part of this network is like any network whatsoever. In the paper, they use an AlexNet-like architecture, so we'll kind of stick with that as well. And you'll notice that the first few layers are kind of in this red box here, and then the last layer here, which actually does the classification stage, is outside this red box. What I suggest is that you take the first part of the AlexNet and wrap it around a sequential model so that you can just pop in an input image and out pops the last feature that comes out here. So the features from the AlexNet architecture get fed into this kind of sub-little network shown here. So this is kind of your attention part. It's a two-layer, multi-layer perceptron, so two linear layers with a tanh in between them. And it will take the features from your AlexNet architecture and weight those features. So the output from here will be a one length vector, and it will just weight each of the features that you have provided from here. So for example, if you had 256 features in the last layer in this mini network, out of here you'll get a one-dimensional 256 length vector which has weighted all those features. And then finally, finally you have the last part, which I'm going to call the classifier, and I do believe in my comments on the Collab notebook I call it a classifier as well. And that will take the information from both the two-layer multi-layer perceptron as well as the AlexNet features, combine them through this multiplication function here, and pass it through the classifier. You'll notice that there's an additional operation here, a plus operation. So it's there if you're going to push multiple feature outputs into this two-layer multi-perceptron. Just to start off with and to get started, I suggest you just take one feature layer, so pass it through this AlexNet and just take the last one here and pop it through here so that you only have to do the multiplication stage and you can ignore this plus stage just now. And then once you have that up and running, you can kind of adapt your AlexNet so that it outputs multiple features, and then you can do some addition later on. All right, so basically today you've got an attention model which is in your Collab notebook. We've kind of set out most of it for you so that you can go straight into the class called attention and start building up these three different architectures that I talked about. So you're going to have an AlexNet, which is going to be most of AlexNet up to the last convolutional layer. You're going to have the second part of AlexNet as a separate network, which is wrapped around another torch.nn.sequential model. And then you'll build this two-layer multi-layer perceptron, again wrapped in its own little model. So the two-layer multi-layer perceptron will have this kind of architecture. And so you'll have the feature size, which is the 256 features that I talked about a couple of minutes ago. You'll have whatever layer size you decide to put in your attention model, which is here. This is up to you. And then the output is a one length output. So this will be your multi-layer perceptron. If you get stuck, please feel free to ask your TAs. They've been through the code already and are very familiar with what to do in each of these networks actually. I just put a note here for myself as well. When you're running the model and training the model, you're going to call these models inside the forward function. Remember to apply softmax to your multi-layer perceptron output so that it sums to 1, and so the weights are sufficient to apply to all your features. Okay, so just to give you a quick overview before you leave and do this, you have output length from the AlexNet architecture will be 256, if 256 is the number of features that you set, times n, where n is the number of, is your batch size, it's the number of instances you have in a batch. In here, you'll have a 1 by n output, and, oh, I believe I may have got something wrong here. You'll have a 1 by n output here, and then when you multiply them, you should eliminate the nth term and have a 256 layer output there. So when it goes through the classifier, you've just got a single instance there, or that's how it perceives it. And that should give you a single score at the end for all of the images that you've popped through. Okay, so that's the architecture part of the model. And now we're going to talk about the data set. So in the Collab notebook, I quickly implemented the MNIST bag, which was described in the paper. So the MNIST bag has 2 labels associated with it, even though MNIST has 10. But kind of just ignore the fact that MNIST has 10 digits inside it. So one bag is labeled, one label is 1 and the other one is 0. So it's a binary classification problem. And a bag which contains a 9 is called 1. A bag that does not contain any 9s is called 0. It's a very simple bag toy implementation of bags. So in the Collab, you should be able to run a couple of cells and actually see this kind of output. And so here we've set the number of instances to 10. So each bag has 10 digits in it. And if one of the 10 digits is 9, then we label it as 1. If none of the digits are 9, we label it as 0. And this will let you kind of play and toy around and play with your model as you're building it. In addition to this, I've also put together a real-world data set which mimics the data set that they used in the paper, but this is slightly different. It is a cancer classification data set, so we took a subset of the PCam data set. So CAM stands for Camelyon, which was a popular challenge ran in 2016 and 2017. And they've all got little patches assigned to them. So it's the same thing though. They had a whole slide image and they randomly took patches from this whole slide image. So we know which slide it came from as well as the patches themselves. And I just randomly took 100 patches from each whole slide image and put them in the same structure as the MNIST-BAG dataset. So you can easily load them in and use them in your model. So this is a whole slide image, and they took tiny little patches from it. They do give the labels right at the patch level if you want to validate your method and see if it's working better at the patch level and if you can get instances that are quite accurate. But for now, you've just been given cancer and healthy. So cancer is assigned a label 1, healthy is assigned a label of 0. So I wanted, before we ended, I just wanted to give you an intuition as to why you would want to take lots of patches from an image and push it through a network like so, as well as being able to put an entire image through a classification network. The idea here is really to increase throughput in a pathology laboratory. So just now when pathologists have to go through slides, I think something around 90% of slides in a traditional pathology laboratory are all healthy. So a lot of the time the clinicians are just going through lots of healthy pieces of tissue. So if you could limit that down to just the ones that they need to look at and the ones they need to look at manually and really dive into and write a report for, then that could really increase throughput and really increase their workflow. Also, I talked about this example earlier. If you wanted to do cancer subtypes, only some patches in a slide would help you do that cancer subtype classification. You don't want to look for lumps of cells, rather you want to look at how the cells are behaving inside the entire organ or body part or whatever slice you have available. So really you need to find a way of defining the relationship between all the patches within a single slide. So there's a lot of scenarios in pathology where you need to know this level of information at the slide level, and I'm sure you can find a lot more examples out in other real-world data sets as well. I would be happy to discuss them further. And I think that's it actually for me. I'm going to let you guys get started, and then we'll update you as you go along. And if you have questions, feel free to have them come in. I will be on Slack for a few minutes longer to give you the link to PCam if you want to get started on that. I have a feeling most of you will want to get started on MNIST-BAG and then maybe go to PCam after. I will say though that this link to PCam will not be here longer than a few days because it's 3.32 gigabytes and I don't have a lot of space left on my drive. So it will disappear after a few days, so grab it whilst you can. And with that, good luck. Feel free to ask questions. Hopefully you've had some time to look over the Collab Notebook and really get an idea of the data set that you're working with, the MNIST one at least. So here I very quickly just did a schematic diagram of the three models that the three sequential models that you'll be building and that I commented in the Collab Notebook as well. So here you have your input X going into a couple of convolutional layers and a couple of max pooling layers as you would do in the AlexNet architecture. And you could put a couple of linear layers here just to flatten out all of the features. And that was a 256, the last layer that I was talking about earlier. Then what happens in the forward function is that this gets passed as input to your two-layer multi-layer perceptron. So here's your two layers here and they're separated by a tan H. And note that this is 1, so it's the input is a 256 by n, so where n is the number of instances. So when you make this 1, it's actually 1 by n output. I believe I said 256 earlier. So 1 by n output from this from the two-layer multi-layer perceptron. And then when it comes to the forward function, you will call your base model, so your base AlexNet model. You will call your attention model, but after that, you're going to multiply the two together to give you another matrix which will be passed into the classifier, so the last bit of the AlexNet architecture. I was looking around and most of you have actually got through most of this architecture, so I think it's pretty clear to everyone, it seems. So we've actually updated the Collab Notebook kind of with these three architectures in it. So I'll just show you that now. So here's the build AlexNet end, which is just the last layer of AlexNet, which will give you a 1 output because we just want a single integer, remember, for this entire bag, for this entire batch, just a single integer. That's the AlexNet there, the 2-layer MLP. And in here we've called the base model and got a hidden embedded representation from it, passed it into our attention model, got our attention weights from it. And then I just added this here. So this is, before you multiply the two together, you do need to transpose it because that will get rid of the n dimension there. So please do transpose the output from the attention model before you multiply it. That might trip you up. But then after that, you'll pass it through the classifier and you should be able to get a single integer from it. So I'll let you do that before we update it again. And for those of you who kind of got through most of that, I just want to end off by talking about gated attention. So by the end of this practical session in the Collab Notebook, you'll have the implementation for the basic attention without gating, and then one for gating, which is why I had the variable self.gated, and it's a Boolean variable. Yes?
What is gating?
What is gating? We're going to talk about that now. So gating is a mechanism that was kind of that was stolen from the LSTM community, so the community working on recurrent neural networks. And it was a way of letting through certain amounts of information, but not all the information, so that you could forget information earlier on in time points, and you can retain information, update your internal states, see more of your environment, or see more of a text or a document, and then again update your internal state. So it was a mechanism for allowing certain amounts of information, but also allowing to forget certain amounts of information as well. And that was important because you can memorize everything, or else you know there'd be information from, I don't know, 10 days ago that you're just not interested in anymore, and you need to take that into account when you're updating an RNN. So RNNs are based on temporal information. Here we don't have temporal information. So the gated unit that you use with the MILAttention pooling is actually it's much more simpler than an LSTM. You won't actually need an LSTM at all. However, when I say they stole the sigmoid part of this attention, well, this gated mechanism. So
Tensor product, no?
this is, sorry?
Are those convolutions and tensor products or multiplication?
They look like exactly what you would see in a convolutional layer, which is a common. It looks exactly like that, but here they are just linear. They're not convolutions.
So the star is matrix multiplication.
It's a multiplication. So this is the hidden representation, and this is our gated part, which will weight that hidden representation.
It's not matrix. It's like point-wise multiplication.
Yeah, so it's a linear.
The one in the middle.
Yeah, one in the middle. It's point-wise.
Oh, yeah, sorry. This is an element-wise multiplication, yes. Sorry, no, absolutely. So you have an element-wise multiplication here. You have a hidden representation, your features or whatever you want to learn within the gating unit, and then you have the sigmoid, which weights, which lets in certain amounts of information and doesn't let through others. So it's a weighting mechanism as well. So this is more commonly known as gated linear units. In the paper that I gave you, there was a reference to Dolphin et al., I believe, and in there they describe glue and refer to the original naming in that paper. It's a really interesting paper, actually. I had a quick glance through it myself. Oh, it's right here, Dolphin et al. So if you want to get into in a little bit more detail, feel free to look at that paper. But yeah, if you've done the attention part already, I'd highly recommend trying this out. I think I mentioned in the lecture that the results were actually, you know, they said it was on par in the results section, but there was slightly worse performance when they used gated attention. So in my eyes, it only works for certain problems. So it worked for their toy dataset, the MNIST dataset, but didn't work so well for their cancer datasets. So sometimes it may not even be worth putting on gated attention. a gated attention unit. I think personally it's because the two-layer multi-layer perceptron is already applying attention to your network, and by adding the gated attention, you're kind of putting attention on top of attention, and I don't know how much more information you're going to get from another gated attention on top of what you have already. So personally, I think that's why they didn't get much more by adding this implementation. But I'd actually be really interested to see what you guys think as well. Feel free to try it out. I believe Willie did yesterday, and he found like a 3% improvement. He can talk to you guys online about that. So with the MNIST one, you might see a slight improvement. So yeah, please go ahead and give it a go. All right, guys, so we've given you a fair bit of these 3 hours to get stuck in. Hopefully you've managed to at least get the basic attention model up and running. The code has been updated, and we've provided... Oh, I did. The code has been updated. So you can see the updated code on the Collab Notebook. So we've added the softmax function, which applies the weighting to the output from the two-layer multi-layer perceptron, and simply multiplied it as well, and then that gets pushed into the classifier. So just a few additional lines of code are added. In addition to that, we've also added some gated MLP model as well here using the glue that I talked about, which is actually built into PyTorch, so you need to do very little in order to add that gated linear unit. Feel free to play around with it, try different number of epochs. I found that maybe with 20 epochs is too much. You might overfit with that 20 epochs there. So maybe try and reduce that when you're using glue as well. So the last thing I wanted to mention was the dataset that I gave you a link to on Slack contains 146 bags, which is not a lot compared to the MNIST toy dataset that you were working with. But those patches were extracted from 146 patients. You know, it's quite a large number of patients, and realistically, this is what happens when you're working with real data. I've been playing around with it during this practical session, adding some dropout, you know, very quick things to try and get my model to avoid overfitting. I haven't managed to get very good results with that particular data set, and my suggestion is actually to go back to the PCam webpage, the GitHub repo, and re-downloading it and re-extracting some more patches. So we limited it to 3 gigs because of our limitations with, you know, Google Drive, etc. But what I've done is on the week 3 folder, I've given you this PCam prepare file, and that's exactly how I extracted the data in the first place. So you can rerun it, you can change the number of instances per bag, you can try it out with the train, validation, and test set and put it all together to create a bigger data set. It's all there for you. So if you have any questions or something's wrong with it, please feel free to get in touch even after this workshop. And I think that's it for us today. I want to end off by saying a big thank you to my TAs, Ali. Yay. Thank you for being a great TA. And also Willie online. He's been really great with walking you through all the code as well online. So thank you very much, you two. I hope you guys have all taken away something from this workshop, at least a couple of ideas from the lectures. It's definitely a different way of thinking about traditional supervised learning and adapting it to work with your problems. And with that, I think we'll close for the session. Thank you very much.